So finally, I kind of want to talk about pseudo-labeling here. And pseudo-labeling is actually a very simple technique. I'm sure some of you have probably used it without knowing you were using pseudo-labeling. So we'll get into a very brief explanation first. So pseudo-labeling is fairly simple. So we have in pseudo-labeling, we assume we have an unlabeled data set and a labeled data set. And initially, all we do is train up a model on solely the labeled data. And what we might do here as well is do some augmentation and kind of build up as much information as possible from the labeled data when we do train this model. And then once we're satisfied that it's learned sufficient information from the labeled data, we push our unlabeled data through this model and come out with pseudo labels. So these labels, we don't know if they're correct, but we do know that it's learned from this particular data set. So we know that at least some of these instances will have accurate labels assigned with them. And then we kind of retrain the model, so this particular model here, using both the pseudo-label data and the labeled data. And together, they should give a stronger model, especially if the unlabeled data contains some sort of variations on the labeled data. So for example, if we have images of cats and you have different types of cats in here than you had in here, your model has learned some additional information about what kind of shape and sizes those cats can take. Whereas if we left it just to the labeled data set, it's not captured any of that abstraction or variation rather. Whereas with just the labeled data set, it hasn't captured that level of variation. It's important to know that here we're assuming that the labeled data set and the unlabeled data set do share some sort of similarities. We can have severely high variability between these two data sets, because then your pseudo labels are likely to be very incorrect indeed. So you need to be careful about not having the unlabeled data too different from the labeled data set, but also share some sort of commonalities as well and contain some sort of variability, so that you're getting additional knowledge when you include some of the pseudo labels. So it's a very simple technique, and I'm sure I've definitely seen it used in challenges. So in challenge data sets where you want to boost the performance just a little bit more. And this technique seems to be used quite a lot because you can use data that's out in the public but has not had high labels associated with it, and kind of reuse it for this setup here. So if you're doing a challenge and you want to just get another 1 or 2% accuracy boost, this is a really good way of doing that. So I came across one particular adaptation of pseudo-labeling when I was doing my research, and it was called MixUp. And it was a really interesting technique because instead of just pushing unlabeled data through our model and gathering pseudo labels, it did do that, but it also recorded what kind of pseudo labels it was getting as it was training the model as well. So by gathering all of the probabilities for every batch and every epoch, what they could do after it was done with the pseudo-labeling task, it could look at the record of all the past predictions and update all of the pseudo-labels, and so that they were stronger and therefore a bit more confident in the predictions. They also had a regularizer, so that at the start of training, when the model had not seen a lot of data, we would limit the confidence of those pseudo labels. But as the model saw more and more data, the confidence grew and grew and grew. And I thought that was a really interesting take on a traditional pseudo labeling technique approach. And so the name MixUp actually came from the additional data augmentation and randomization they added, because they found that by just doing this particular approach, they overfit quite a lot to their data. So they had to do a lot of augmentation and randomization in order to complement the pseudo-labeling technique they had in the paper. But it's a really interesting take on a traditional pseudo-labeling technique. So whilst talking about pseudo-labeling, I think it's important to mention this idea of co-training. So co-training is instead of having two different data sets and kind of supplementing your information with another data set. Here we have two different networks, and they call them views actually. And you may not just have two, you can have more than two. But the idea is that those two different networks have identical architectures and perhaps even shared weights as well. And by training up a model and by pushing information through them, you'll get some differences, but overall they both should perform really well. So it assumes that the network that you're using is intelligent enough to work well most of the time and will only agree sometimes on some of the tricky instances within your data set. So it's ideal for deep learning actually, because we know that deep models tend to perform well on the majority of data. It's usually on one or two instances which are outliers or just not normal things that we would see within our data set that they would disagree on. So it's combining the strength of two networks or more in order to create really good predictions. And this was adapted from Bloom and Mitchell's work in 1998, so before the deep learning boom that this work came out with, and they were tested out with much smaller classifiers and much smaller networks. So this paper here is called Coteaching, but it's a type of co-training architecture. And what they do here is they have two different models, A and B, which are shown in this diagram here. And they only really train A as you would do normally, put images through here and feed it through the architecture. And when they come across instances which have a low loss, then they feed that through model B and update the weights in model B. So the intuition here is that if you have an instance which has a low loss, it's more likely to be correct. And therefore, you're training a model that's seen very, very good examples within your data set and has not seen those examples which are causing confusion within model A. And therefore, you have a model which is resilient to noisy labels and then a model that is as normal as you would normally train a model architecture. So you're almost getting additional information just by feeding in specific instances into another architecture. But what I really liked about this particular figure here was that they compared it to other techniques such as decoupling, where you have your normal architecture and they only ever update model B when so both instances go through A and B. If you have a particular instance or a particular image, it will go through both models. And only when they disagree do we update model B. Otherwise, it stays the same. So again, it's kind of supplementing your one model with another model which has a slight tweak to it. So this is co-teaching and co-training. It's the ability to share weights or to share networks and instances between multiple models, which are essentially identical. However, whilst I was doing research on this particular topic, I came across this paper from, I think it was 2019 actually, maybe not 2009. But it was a really interesting paper because they had a deep dive into co-training and looked at the original paper by Bloom and the assumptions that they made in that paper. And they actually showed that whilst co-training works when you have a very large data set, in actual fact, and it works actually very, very well with large data sets. But really, you would only choose to use co-training if you had much smaller data sets and you were having trouble actually learning something with a very small data set. And they found that when you have a limited training set, it doesn't work very well at all. In fact, they don't recommend you use co-training with smaller data sets. So I would caution you when you are using co-training, because there is definitely some evidence out there that shows that it doesn't work when you have very small data sets. So moving on, I kind of wanted to end pseudo-labeling with this really interesting technique because it's something that I've never seen before, and it's an out-of-box thinking for labeling data sets. So it's a particular GitHub repo called Snorkel, and you can install it with just pip install. And it has a really nice library available to create what they call labeling functions. So the idea here is that instead of assigning labels to each instance or even a group of instances and kind of attaching specific definitions to each instance as well, what we can do is actually build a program that can take an instance and then just return a label associated with it. So here on their website, they actually give a really nice example with spam, so detecting spam within your mailbox. And they've created some small labeling functions that if you see specific terms like my, because if someone's talking about my channel or my video, check out my channel, my video, then you would return that it's a spam it's a spam mail. And similarly here, if you see check out, then again, return that label spam. And I think this is a really interesting way of coming up with labels, because I know in the medical field, for instance, if we were looking at cells, and we know that elongated cells are lymphocytes, but very round circular cells are more likely to be either healthy epithelial cells or even cancer cells if they're really big and abnormal looking. So I can see that being implemented within a labeling function. So for example, if you were given a circle and you looked at the major axis and you knew that it was bigger than the minor axes, then you know that it's elongated. So there's a mathematical way of actually encapsulating that knowledge. And I think it's a really interesting way of moving forward with our idea of labeling. And it's a unique way of labeling data as well. So feel free to check it out. I might check it out myself for my research further down the line. And yeah, it's just another take on pseudo-labeling, I guess. Just very, very different. So that concludes kind of the main content for today. But before I finish up, I just wanted to mention a few other learning techniques, starting off with active learning. So active learning is a really, it's a different way of providing your model with data. So typically what you would do is just gather as much data as possible and then push it through a network. But in active learning, you're actually being a bit more smarter about what information you feed to the model. So you would give the model some information and the model would learn and update. And then it itself would tell you either by grabbing more images from a pool of data or actually generating new instances and asking the human to label those instances. And the idea is that by having the model actually pick and choose, it's going to pick instances which are likely to improve performance. And therefore, by iteratively going back and forth between a human and the model itself, you're actually boosting the accuracy rates by being more selective about what you're feeding through the model as it updates over time. And it may work for some settings, but it may not work for others. I know that certainly within the medical field, we can iteratively ask for data if we were setting up a research problem. But really, if you were going to implement a product and put it into practice, that's not feasible anymore. So yeah, you need to be quite selective about when you use active learning, but it may work for some instances. Online learning is something that you're all familiar with, and it's when you you're provided with data over a time period rather than, again, all in one go. And the job really here is to update your model as data is made available rather than wait for data to come in all at once and then push it through a model. And really, this is what the entire reinforcement learning field is all about. You know, when you put a robot in a scene and it's collecting video feeds or sensory inputs, it's kind of aggregating information as it sees things and then updating its internal state in order to recognize this 3D that is being placed in. So there's an entire field on reinforcement learning and the type of architectures there. And if you're within that field already, you're probably already familiar with all of the techniques there. Another type of learning modality is multitask learning, which has been gathering a little bit more speed recently because you know, a lot of people have found that a lot of the tasks that we're solving, there's a lot of crossovers, and a lot of the features that you would learn within one task can be easily reused within other tasks. So for example, if I was taking a medical example and I was looking at breast tissue, you know, the task of cell segmentation and tumor segmentation are very, very similar. You know, you still need to learn about stains, the stains that are included within the tissue. You still need to learn about what a cell looks like. You still need to learn about what connective tissue looks like. So, at least the first part, creating the abstract features and creating all those layers at the start of a model, they would be identical for each of those tasks. So here in multitask learning, we're kind of sharing the knowledge between lots of similar tasks, and then only adapting the final few layers, or here the decoder element of a variation autoencoder, to perform each task individually. And again, that is very depending on the application, and depends on what exactly you're trying to solve and whether you can get those additional data sets that can complement your task as well. So to finish up, I just want to roughly go through the pros and cons of each. So self-training, which we talked about right at the start, is obviously very simple to understand. You know, it's quite intuitive. A lot of these ideas came from human observation and looking at what humans do, and then transferring that knowledge to the deep learning field. And the ground truth here is absolutely free. You don't need to collect additional data here. So you can almost bucket it into unsupervised learning techniques as well. The cons here is that mistakes can reinforce themselves. So if you make a mistake earlier on in the training process, that'll just kind of reinforce itself as training continues on. And there's really no way to get out of those mistakes once they're made. So do be careful with self-training. And usually if you have enough data, you can avoid making those mistakes in the first place. And so secondly, I talked about multiple instance learning, where it's very useful in scenarios where you know you need some knowledge from an expert, so such as in the medical domain, where you know that just even a tiny bit of knowledge from an expert could help your model. And it's appropriate for both non-imaging data and imaging data. It's definitely being used in text data a lot. The original paper from 1997, which talked about multiple instance learning, they were working with drug discovery techniques. So they were looking at molecules within drugs. So if you're working with non-imaging data, definitely have a look at multiple instance learning. You'll find a lot of different types of techniques out there for lots of different types of image data. Non-image data. Now, the downside to that is usually that you kind of need to sit down and rethink about your problem. And not only that, you also need to re-implement your problem such that when you're loading data, reformulate it and put it into bags. So that takes time to actually do that implementation in practice. However, once it's done, you know, it's done. You can kind of change the model and architecture however way you see fit, and everything else should work as is. Also, the aggregating tasks, so all the mill pooling techniques that I talked about today, is very task dependent. So sometimes max pooling will work if that is what is needed in order to solve your task, but sometimes it won't. And often you need to actually just try out a lot of these techniques before you get to a final conclusion as to what works well with your particular data. And then pseudo-labeling is a really useful way of reusing very, very accurate labels. So if you know you have a small data set and it reflects the rest of your data set very, very well, you can reuse the information within that small data set, and you're basically growing your training set, which is a great thing to see. And because then once you've grown your training set, you can reuse it for other tasks as well. The cons with that is that, again, if you have errors within your labeled data set, it's just going to propagate and grow and become even more of a mess within your unlabeled data set when you pseudo-label them. So if it was, when I use pseudo-labeling, I tend to just do a quick one pass through all your labeled data and just make sure that there's no glaring errors there. You also want multiple instances to share the same label as well. So if you share the knowledge between multiple instances, you've kind of avoided that problem as well. Sometimes it may improve performance, and sometimes it may not. And that really comes down to if your unlabeled data set is very different from your labeled data set, or if it's only a little bit different from your labeled data set. So obviously, if it's very different, it may not improve performance because the pseudo labels will be awful. But if it's similar, again, it may only add a little bit of knowledge and may not be as much as you wanted. So please be careful with that when you are using pseudo labeling techniques. So that concludes the final lecture for today. I just want to finish off by telling you that all of these pros and cons that I've been mentioning at the end of the lectures, I've put into one document. So it's almost like a quick lookup table if you're looking at different techniques. And we'll make that available on Google Drive. And also the reading material, which you were given the link to when you started this workshop, has been updated over time as we've been looking at more, as I've been building the material and as we've been looking at more and more networks in the practical sessions as well. So this list has grown. If you've not looked at it since the start of the workshop, I encourage you to re-look at it and have a look at some of the additional links that have been provided. And with that, I would like to thank you all for joining the workshop. I hope you've learned something new and learned some new techniques that you can use within your work. If you have any questions, feel free to bring them along on Thursday. I'll be sticking around after 9 if you still need to, if you've got questions that will take you past the practical session as well. Thanks.